Hi, good morning, class. So today we want to look at section 3.2, which is titled What's Unusual? The Empirical Rule and Z-scores. So we're going to look at the empirical rule for symmetric distributions and also Z-scores, and then also we want to be able to determine if a data value is unusual or not. Right, so here we have a slide on the empirical rule. So the empirical rule is a rough guideline that we can use for approximating percentage of data within 1 to 3 standard deviations of the mean in a unimodal symmetric distribution, right? So remember, the standard deviation is the average distance away from the mean, right? So some guidelines that we have that was presented in the book, right? 68% of the data is within 1 standard deviation, 95% of the data is within 3 standard deviations, and then almost all the data is within 3 standard deviations, right? And actually, when it says almost all, so I'm going to make note of this. This, what we're meaning is 99.7%, right? That's typically the value used, right? So some people approximate this a little differently. But 99.7 is the common value to be used. So it's called this. So we also call this the 68, 95, 99.7 rule. Right? So this can just help you remember those percentages. And then on this slide, I took this from another book, but I think it's powerful. So it's just showing you a normal bell curve, right? And one thing you want to remember is that when you see a distribution shape like this, it's just where you make the histogram bars really, really small, right? So you might have bars that are this big, and then you make them smaller, right? The next time you make the histogram, and then you make the histogram again where they get even smaller, right? And you keep repeating this process so they get really, really small. And eventually what will happen is your histogram will create this looks like a curve, right? So this is a normal distribution, and we call it the classical bell shape, right? It looks like the side of a bell, right? So it's very so the reason why we have z-scores and how they can be useful is it allows us to be able to compare different scores, such as IQ scores, SAT, ACT scores, and so forth, right? So many data sets are normally distributed, and in order to know if something's normally distributed or not, you do have to do some statistical tests to see if does this sample appear to come from a population that's normally distributed, right? But we're not going to get into that, right? That statistical test. So I will tell you if something is normally distributed or not. Right, but you can see right here where it says 0, 1 theta, 2 theta, 3 theta, 4 theta, and so forth. This is my z-axis, my z-scores, right? So there's like a number line here. Right, so there's 4, 3, 2, -1. Well, these are all negative, sorry. 0, 1, 2, 3, 4. Right over here. So when we say within 1 standard deviation away, we mean 1 standard deviation to the left of the mean and to the right. Right? So all of this shaded yellow would be within 1 standard deviation. Right? So then to go 2 standard deviations, right, we would have to go 2 standard deviations to the left and to the right. Right? So the yellow and the green would be 2 standard deviations away, right, and so forth. Also notice that the percentages, so if we go from 0 to 1, the percent is 34.3% on this diagram. It is also 34.3% to the left, right? It's normally distributed, meaning it's symmetric. So it's going to be the same area on both sides, right? Also, something to note is that the total area under the curve is 100% or 1, right? So we can use that to help us sometimes too, right? So everything underneath would be 100% of our data, right? Right. Right. One thing just to remember is that the z-score, right, equals the number of standard deviations, right, away from mean, right? So we're going to see in a little bit, but to calculate a z-score, what we do is it's a ratio where we take the x value we're looking at minus the mean, and then divide that by the standard deviation, right? So this is how we calculate a z-score. It's just the ratio of the distance away from the mean compared to the average distance away from the mean. So we're trying to, so since we're taking the distance and then dividing it by the standard deviations, we're trying to see, well, how many standard deviations is it away from the mean, right? And this gives it a specific z-score, right? So that's what we're talking about here, right? So this this empirical rule, we're going to do an example of that. So it says data on smog levels in a sample of cities was collected and the distribution was found to be roughly symmetric and unimodal. So that means that we can apply the empirical rule, right? So the mean of a particular level for the sample was 10.7, right? So the mean was 10.7 with a standard deviation of 2.6 micrograms per cubic liter, right? So my standard deviation, my S, is 2.6, right? So I believe these are this is the example we did in the last section, right? But we're using the empirical rule here. So if we look at this with the empirical rule, right? So in between one standard deviation, we have 68% of our data. Within two standard deviations, we have 95%, and then nearly all, or 99.7, right? 99.7% will be within three standard deviations of the data, right? So within three standard deviations, 99.7% of the data will be within that range, right? Right. So we calculated these standard deviations previously, right? Remember, these are referred to as z-scores, right? So we often show, so if you have a z-score of 1, right, this corresponds just to one standard deviation, and typically we'll use 1 theta, right, for the population symbol for population standard deviation, right? So if we have a axis with z-scores, right, then 0, this is the mean, and then if we go 1 standard deviation away, that's z-score of 1, another standard deviation away, that would be a standard z-score of 2, right, and so forth. But we can also show that as 0 theta, 2 theta, right, however you want to show it, right? So depending on the text you're using, that all means the same thing, right? So if this was my z's, right, so if I use this line to represent z's, this would be -3, -2, -1, 0, 1, 2, and 3, right? And you might be wondering where these values came from, right? I believe we calculated all of these in the previous section, right? But just to remind you, so standard deviation, whoops. So so we know that x bar, the mean, is 10.7 from before, right? And the standard deviation is 2.6. So if I want to go 1 standard deviation out, right, it means that there is 2.6 in between here and here, right? 2.6. So I need to add, so I need to take 10.7 plus 1 times 2.6 if I want to go 1 away, right? So this would give me the 13.3, right? If I want to go 2 out, right, I would take the mean 10.7 plus 2 times the standard deviation of 2.6. And that's where I get 15.9, right, so forth. So we can keep doing this to get these x values, right? So remember, we just manipulated the equation. So if we have the equation all right, So continuing on with this example, we're told that about 68% of the cities will have smog levels between 8.1 and 13.3, right? So this is 10.7 plus or minus my standard deviation. About 95% of the cities will have smog levels between 5.5 and 15.9, right? Which is 10.7 plus or minus 2 standard deviations away. And then almost all the cities will have smog levels between 2.9 and 18.5, right? Which is taking the mean 10.7, adding, subtracting 3 standard deviations away, right? Remember, my standard deviation is 2.6 here, right? Right, so here's another example of temperatures. So it says the mean daily temperature in San Francisco is 65 degrees with a standard deviation of 8, right? So my mean is 65 degrees and my standard deviation is 8 degrees. So we're asked to find the temperatures ranges for 68, 95%, and 99% of the data, right? So to find 68%, right? Remember that this is 1 standard deviation away, right? So if here's my number line, right? Here's my mean. I want to go 1 standard deviation this way and 1 standard deviation this way, right? So this is negative 1 standard deviation and positive 1 standard deviation, right, away. So I know the mean, this value is 65, and I know that the standard deviation is 8, right? So I need to add 8 to get to this and then subtract 8, right, to get to this one, right? So 65 plus 8 will give me what? 73, right? So this would be 73, and then 65 minus 8 would be what? 57, right? So this would be 57. So in between 57 to 73, we can expect 68% of my data. Right, so going on the next slide, I have those calculations for you. Right, so you would do the same thing for 95%. Right, so to find 95%, you want 2 standard deviations away. Right, so if you're more visual, you can draw a number line. Right, so again, here's my mean. Here's 1 standard deviation away. Here's 2. Here's 1 standard deviation away. Here's 2. Right, so between here and here would be 2.6 units. Here and here is 2.6 units. So to find this leftmost value, right, what I need to do is take my mean, subtract away 2 standard deviations, right? So my mean was 10.7, and my standard deviation is 2.6, right? So if we simplify this, that's where we can get 49, right? 49 degrees. So this is 49 degrees, right? So then to get this rightmost value, right, we would take x, my mean, plus 2 standard deviations away, right? So this would be 10.7 plus 2 times 2.6, right? So that's where this 81 is coming from, right? Because we went 2.6 this way, 2.6 again this way, and remember right here in the mean, this is 10.7. Or excuse me, I'm looking at the wrong notes. I apologize. Right. So let's scratch that. I was using the mean and standard deviation from before. Right. I was wondering why these numbers are not adding up. Right. So same concept. I was just using the wrong mean standard deviations. Right, so if we have a number line, right, if we want to look at the, for 95% of the data, right, here would be x bar. Over here would be -1 theta, right? 1 standard deviation away to the left, and 2 standard deviations away to the left, 1 to the right, and 2 to the left, right? So my mean here is what, 65, right? And my my standard deviation is 8, right? So right here is 65 degrees. So in order to find 2, right, I'd have to go 8 units to the right and then 8 units to the left, right? So to get this value, it takes 65 plus 2 times 8, which gives us what, 81, right? So this is 81 degrees. And then to find the one to the left, right, this -2 theta, we would take 65 minus 2 times 8, right? So 65 minus 16, which gives me 49 degrees Fahrenheit, right? So this would be 49 degrees, right? Because we went 8 and then 8 more, right? Because that's my standard deviation in this case, right? So you can see this table fills in the rest, right? But that should help you know how to do it, right? So you can use equation, right? So if we take the mean and then add on the z-score, the number of standard deviations away we want to be, and then multiply by the standard deviation, then this will give you the new x value, right? So remember, these are the z-scores, right, which are just these numbers. Right, so then number 2 says, so since 95% of the daily temperatures are between 49 to 81, according to the empirical rule, only 5% of the temperatures are outside this range. Due to the symmetry of the distribution, right, that means that we'd have, so let me draw a picture of this really quick, right? So here's my distribution, right? Right, so here's my mean of 65 degrees, right? Here's 1 standard deviation, here's 2 standard deviations away, right? Here's 1 standard deviation away, and here's 2. So what we found is we looked at the area in between, or what we're talking about is the area that's 2 standard deviations out, right? So all this yellow, right? So this represents 95% of my data, right? So what we're saying is, if 95% of my data is in between these two ranges, then if you take 100%, which would be the total amount of data, minus 95%, that leaves 5% of my data, right? But notice I have 2 parts. I have a part here and here, right? But since this is symmetric, right, that means the same areas on both sides. So this 5% that's left has to be divided by 2, so we get 2.5%. So that means that 2.5% of my data will be here to the left, and 2.5 will be here to the right, right? So 2.5% of my data is above 81 degrees, and then 2.5% will be below 49 degrees, right? That's what that's saying. So having a temperature colder than 49 degrees would be very unusual, right? It's not going to happen very often, right? So things that are near the mean, these are going to be your typical values, right? Things that happen a lot, right? They're more frequent. So next we're looking at z-scores, right, which I've talked about briefly before. So these are measures of how many standard deviation observed value is from the mean, right? And I already connected this to standard deviations and gave you the equation, right? I think it all flows together very nicely. This empirical rule and z-scores, they really are very close together, right? So an example is a z-score of 1.5, right, means the observed data value is 1.5 standard deviations above the mean, right? A z-score of -1.5 means that the observed values is 1.5 standard deviations below the mean. Right, so here's an example of a dot plot. And we have the z-scores listed below here, right? So here are my z-scores. So it says the dot plot shows the heights for a sample of men. How many men would have z-scores greater than 2, right? So here's the cutoff for z-score of 2, right? So how many are above or greater than? There's just 2 values, right? So there's 2 scores, right? Remember, each dot represents every data point, right? So there's 2 dots, so 2 people are greater than 2 standard deviations away from the mean. And then we can look at, well, what's less than -2, right? So it's doing the same thing, but we want to go to the left of -2. So there would also be two data values, right? Less than -2. Right? So there's just the solution that we already did. All right. So here's an example of z-scores. So remember, this is an important note, is that z-scores are unitless, and they're this what we call a standardized measure. So z-scores can help us compare observations in different distributions, right? So if I compute z-scores in one sample and compute it with another sample, we're able to compare them, right? We're able to compare the different distributions. So this example says, suppose road A has a mean speed of 60 miles per hour with a standard deviation of 5 miles per hour, and road B has a mean speed of 60 miles per hour with a standard deviation of 10 miles per hour. Is a driver going 70 miles per hour on a road traveling A relatively faster or slower than a driver going 70 miles per hour on road B, right? So let's write this down, right? So I have road A and road B, right? So remember my z-scores, right? I take my x value minus my mean and divide by my standard deviation, right? So for road A, so the mean speed is 60 miles per hour, and the standard deviation is 5, right? For road B, the mean is also 60, but the standard deviation is 10, right? So I want to find the z-score for the x value 70, right? So oftentimes we'll put a subscript with the z value, and that helps us just remember what x value we're plugging into it, right? So a z value for the x score of 70 would be this, right? We would do 70 minus the mean, so minus 60 divided by 5, right? Then over here, we would do something similar. So we take the 70 score minus the mean, but we divide by 10 this time. So this would be 10 divided by 5, which is 2, right? And then over here, this would be 10 divided by 10, which is 1, right? So since 2 is greater than 1, this person would be going relatively faster, right? This person is further away from the mean, right? So on the next slide, we have the solution. So although both drivers are traveling 70 miles per hour, the driver on road A is traveling relatively faster, since 70 miles per hour is 2 standard deviations above the mean on road A, and only 1 standard deviation above the mean on road B, right? So road A is going relatively faster. And here's the formula for the z-scores, right? Just again, so the numerator is we're finding what's the distance from the mean, and then we're dividing by the standard deviations. So that tells us how many standard deviations are we away from the mean then. Right? So I have another example for z-scores. So it says Marie scored 80 out of 100 on her first stats exam in a course and 85 out of 100 on her second stats exam. On the first exam, the mean was 70 and the standard deviation was 10. On the second exam, the mean was 80 and the standard deviation was 5. On which exam did Maria perform better when compared to the whole class? Right? So to figure this out, right, we need to write down some notes. So we have what? Exam 1, exam 2. So on exam 1, we got an 80, and on exam 2, we got an 85. The mean on exam 1 is 70. Standard deviation is 10. Over here, the mean was 80, and the standard deviation was 5, right? So if we plug these in, right, so if I find the z-score of 80, we would take the mean, which is 70, or excuse me, we take the x value, which is 80, minus the mean, which is 70, all over standard deviation, which is 10, right? So just a reminder over here, there's the z-score formula, right? So I simplify this, I get 10 over 10, which is 1, right? And then over here, I would do a z-score of 85. So I would take 85 minus 80 divided by 5. So this would be 5 over 5, which is also 1, right? So now my z-scores are the same. So it means that I didn't do better on either exam when we compare to the whole class, right? So here's the solution, right? So the second exam may have been a little easier, but we're still like we're in the same spot as we were before, right? So equally well when compared to the rest of the class, right? So here's another example I want to do. So this is a classic example when looking at z-scores, is we can compare, like I was saying, compare things from different data sets. So one common use of this is being able to compare like ACT and SAT scores, right? So here we're looking at admissions office, and one applicant has a math score of 640 on the SAT, and the other has a ACT score of 28 on the math. But we want to know who has a better score, right? So we have ACT and SAT over here, right? So with the SAT, we just need to note that the mean is 22 and the standard deviation is 5, right? And the source I got this from, they use SD for standard deviation, right? But remember, typically we use just S, but either one's fine with me, right? So in the ACT, this applicant got a score of 28. So I want to find the z-score of 28, right? So to do this, we would take 28 minus the mean and divide by 5, right? And then over here, right, for the SAT, we need some notes. The mean is 500. The standard deviation is 100. And the score is 640, right? So I would take 640 minus the mean of 500, divide by 100. Right, so here I get 140 over 100, which gives me, what, 1.4, right? Then over here, 28 minus 22 is, 6 over 5? So 6 divided by 5 is 1.2, right? So this z-score is bigger, so the SAT score applicant scored higher, right? Alright, so that's all I have for this video. Thanks for your time and patience.